Hello, chemists. It's Jolly again. Let's talk about oxidative cleavage of alkynes this time. Go to our notes. Come on, move. My finger must be too cold to make it move. We'll just go that way. All right, we are going to talk about these last two for alkynes, and I want to point out, don't forget, that's just ripping the hydrogen off of the end of an alkyne. That's just an acid-base reaction. All right, so we're going to talk about oxidative cleavage of the alkynes. All right, we're going to do it two different ways. Now, the reason that I didn't talk about it when I was doing the alkenes is because if you were to cleave an alkene, you only break through two bonds. But if you cleave through an alkyne, you have to cleave through all three. And you can't make a diol. So for these, you can make a diol. But with alkynes, you cannot make a diol, so the mechanism isn't quite the same. So we're going to again use the same two. We're going to use ozonolysis and we're going to use potassium permanganate. But the key is we have to cleave through all of them, so we really don't get much of a choice. So I'm going to put a terminal alkyne. Remember, terminal means there's a hydrogen at the end, or the alkyne is at the end. And it doesn't matter in either case, okay? So I can use one, I could do ozonolysis, and then two, break that ozonide with my zinc. Or I could use potassium permanganate, again, under basic conditions with heat. And then, of course, I have to protonate those carboxylic acids at the end with either water or water and acid. Okay, so either of these, we're going to do the same thing. And I'm not going to show you a mechanism. I'm just going to show you how to predict them. All right, so let me get to a different color. Ooh, let's use purple. All right, just like with the alkenes, you're going to cleave the bond and then draw the two pieces. But you have to put three things in its place instead of just two. And so you're going to put a double bond O and an OH. And I didn't leave myself enough room, of course. A double bond O and an OH. So in this case, you do not have a choice with the alkynes. But I do need to show you something special about this one. It only has one carbon, and it's a carboxylic acid. So one carbon, it's given the name 4, okay? So we would call it methanoic acid, but formic acid is, I believe, Latin. This is the one time that it could go further into the oxidation phase. Remember, I told you if there's a hydrogen connected to the carbonyl, it can continue on. Well, the next step in the oxidation world is carbon dioxide gas. So formic acid has the option of being continually oxidized to carbon dioxide gas. So beware, if you have a terminal alkyne and you do oxidative cleavage, could you stop at formic acid? Yes, but there is the potential that it will go all the way to carbon dioxide. All right, so let's try, I don't know, this one. Sorry, alkynes aren't very creative. All right, so if we do oxidative cleavage, we would right there, and we would end up with 2 acetic acids. Again, not very interesting, if you will, but that is how you would approach the oxidative cleavage of your alkynes. Now I want to go to the whiteboard and I just want to do a few examples of both. All right, oxidative cleavage. We can use ozonolysis. Or potassium permanganate. And we have to control that one with temperature. And it just depends on what you want for the end product. So let's see, how about that one? Let's do an alkyne. All right, so here's just 3 variations. We're going to do both ozonolysis and KMNO4 for both of them. And so for ozonolysis, let's do that one in red. All right, ozonolysis, the first step, okay? The first step would be the ozonide, but I'm not going to go through the complete mechanism. I'm going to cleave, and I'm going to draw the, if you will, the same backbone without the double bond. And then what am I going to put on it? I drew too many carbons right there. Eraser. There's only one carbon right there, so I'm just going to draw carbon. All right, and then you're going to put a double bond in its place. And if this is ozonolysis, we have to ask ourselves, do we continue on to make carboxylic acids or do we stop? And with ozonolysis, we stop. So that's what we get. Okay, so we get 2 aldehydes. If we did KMNO4, let's do that in purple. Actually, that's blue. All right, if we did this with KMNO4, we would again get those 2, but with KMNO4, it will continue to oxidize as much as possible. And so this one would go to a carboxylic acid, and this one would go to a carboxylic acid. And that begs the question, should I take this one further to CO2? And generally we do not. Generally we only do that with the alkynes, but it could. Okay, but just for simplicity, I don't usually take the alkenes all the way to carbon dioxide. I only take the alkynes. All right, so let's do this one. Let me see, first red, ozonolysis. Come on. Again, we're going to cleave. Wow, that was seriously ugly. And then put the carbonyls in its place. And ozonolysis stops, so that's how you would end. So this would be 1, 2, 3, 4, 5, 6. If you wanted to draw it out, that's what it would look like. If you were to use potassium permanganate, you would again, 1, 2, but you wouldn't stop, and you would convert them to carboxylic acids. And then the one that we just did in this video was the alkynes. And you don't really get a choice because you have to cleave through all of them. So you would get 1, 2, OH, and HO, 1, 2, 3. Because I had to cleave through all 3, you get carboxylic acids on both sides. All right. So if you have internal, you get carboxylic acids. The terminal, remember, would have this. And that can go on to be oxidized further into CO2. So for the alkynes, I tend to go all the way to the CO2. All right. And that is actually a very short video, but that is the oxidative cleavage for the alkynes. All right. Till next time. Jolly out.